Hi everyone. In this section I want to talk about standing waves. Let's first recall the principle of superposition that says that when two or more waves meet at the same point in space and time, the resulting wave function is the sum of the individual wave functions. Now let's consider sinusoidal transverse waves on a string. When the wave source is continuous, waves will hit the end of the string and reflect, resulting in many waves occurring at the same point in space and time. This results in periods of constructive and destructive interference. At specific frequencies, standing wave patterns can occur. In a standing wave pattern, the wave will alternate between antinodes, which are periods of maximum constructive interference, and nodes, which are periods of maximum destructive interference, where the displacement is zero. The wave function for a standing wave looks like this: y at x and t equals 2a sine kx cos omega t. And this is a really interesting function because the spatial and the temporal components are essentially separated. This first part, 2a sine kx, is the spatial component, and it represents a wave that oscillates between amplitude of 2a and negative 2a as a result of the interference of the individual waves that had amplitude a. Cos omega t represents that each particle in the medium is moving in simple harmonic motion. So what does this look like? Essentially this figure, it would appear to be stationary so that there's no apparent motion of this wave right or left, but each particle in the medium does oscillate up and down. And that's why this is called a standing wave.
In order to derive the standing wave equation, let's consider two sinusoidal waves with the same frequency, wavelength, and amplitude traveling in opposite directions. So for now, let's consider the case where phi equals 0. This will just simplify the algebra. And then we have the sinusoidal wave function for the wave traveling to the right will be y1 at x and t equals a sine kx minus omega t. And then traveling to the left will be y2 equals x at t, a sine kx plus omega t. Okay, so the principle of superposition says that the resulting wave function will be the sum of these two individual wave functions, a sine kx minus omega t plus a sine kx plus omega t. And we can simplify this using this following identity. So sine alpha plus or minus beta, which both of these functions are in that format here, equals sine alpha cos beta plus or minus cos alpha sine beta. So I want to expand this function using that identity. So now we'll have y at x and t equals a sine kx cos omega t minus cos kx sine omega t for the first term, plus a sine kx cos omega t plus cos kx sine omega t. Okay, so if we look at this, what we're left with is these two terms canceling here. We have one positive and one negative, even when we multiply in the a. So then we'll have two of these two terms which are identical. So 2a sine kx cos omega t. So instead of a traveling wave function, we end up with this standing wave function where the spatial component and the temporal component are essentially separated. And let's just note that at x equals 0, which is one end of the string, then we have y at 0, comma t equals 2a sine 0 cos omega t, which equals 0. So this makes sense that the overall displacement is 0 at that first fixed end. Okay, let's look further into this standing wave pattern. So I've drawn one standing wave pattern here. The nodes, again, are these points here of 0 displacement. So the amplitude at these points is always 0, and they show no motion at any time. So we have 2, oh, I'm missing the a there, 2a sine kx equals 0. And in order for us to have this equal to 0, we need kx to be a multiple of pi. So 0 or pi, 2 pi, 3 pi, and so on. So let's further see what this means for x in terms of the wavelength. So we can plug in for k. K is the wave number, which is 2 pi over lambda. Plug that in here. Kx equals 2 pi over lambda x. And then, as I was saying, this has to be a multiple of pi. So n here will be an integer, and I'll write that in a second. Okay, so pi will cancel on either side, and then we end up with x equals n lambda over 2. And n equals 0, 1, 2, 3, and so on. So we have these nodes occurring starting from 0 here at multiples of half a wavelength. So what this means is that the spacing between two adjacent nodes is half of the wavelength. We can write something similar for the positions of the antinodes. So the antinodes are these points here on the standing wave where the displacement is the maximum. So this will occur when 2a sine kx equals plus or minus 2a, or sine kx equals plus or minus 1. If we look at sine, and if you picture this argument here kind of as an angle in radians, then we know that this value occurs at pi over 2, and that's plus 1, and then negative 1 is at 3 pi over 2. And if we keep going, any other multiples of these two values will also give us plus or minus 1. We don't want 0 and we don't want pi because that will give us the positions of the nodes. So instead we need kx equals pi over 2, 3 pi over 2, 5 pi over 2, and we can continue, and we need odd integers here. So we have kx equals k, which is 2 pi over lambda x, and then that's n pi over 2, so that x equals n. I'm just rearranging here, canceling the pi, and I get x equals n lambda over 4, where n is odd, 1, 3, 5, and so on. So what this tells us is that the position of the antinode from x equals 0 here would be lambda over 4. So we have the distance between a node to an antinode is lambda over 4, which makes sense with this diagram that we've drawn, since we're drawing the antinode occurring right in the middle of the distance between two nodes. Okay, let's look again at this standing wave function. So if we're talking about waves on a string, not every frequency of waves will produce standing waves. This is because we have boundary conditions for the string. We've already looked at the first boundary condition, which is that the first fixed end of the string must be a node, since it can't move at that point. So we need y at 0 and t equals 0, and that's essentially going to be true anyway if we have x equals 0. Now for the second boundary condition, we also need the other end here, where x equals L, to also have a node. So we need y at L and t equal to 0 as well. So this means that we need sine of KL equal to 0. So that means at 0 we need sine to have, this needs to be sine of a multiple of pi. We know 0 already, but that gave us the first boundary condition. So KL equals 2 pi over lambda L. I'm just plugging in, this is K here. And then we need that to equal n pi. So we get, with pi canceling, we have L equals n lambda over 2, or lambda equals 2L over n, where n is 1, 2, 3, and so on, any positive integer. We don't want 0 this time because, as I was saying, that gives us the first boundary here. So this will give us the wavelengths of the waves that produce standing waves in this string. So these are the only wavelengths where standing waves will occur. Each wavelength depends on the frequency, and we could also write this instead as the frequency. So the wavelength will depend on the frequency and the speed in that medium. We have v equals lambda f, so f equals v over lambda. So then we can plug in this wavelength here, and we get f equals nv over 2l, where n is 1, 2, 3, and so on. So this is another important relationship here. And this gives us the frequencies at which standing waves occur. So the lowest standing wave frequency that will produce a standing wave is when n equals 1, and this is called the fundamental frequency. So we have f1 equals 1 v over 2l. And that's either the fundamental frequency or the first harmonic. So these frequencies are also called harmonic frequencies. The allowed frequencies at which standing waves can occur are each multiples of the fundamental. We can see that here. So we'll have Fn equals n f1, where n is 1, 2, 3, 4. And this is a complete harmonic series since we have frequencies existing for all positive integers.
Okay, let's imagine that we have a string and we have a frequency generator connected to it where we can adjust the frequency. At any frequency, what we'll find is a pattern of constructive and destructive interference, but at specific harmonic frequencies, standing wave patterns will occur. Those frequencies can be calculated using this relationship, f sub n equals nv over 2l, or lambda equals 2l over n, where n is a positive integer, 1, 2, 3, 4, 5, and so on. And each of these harmonic frequencies corresponds to a distinct standing wave pattern. N equals 1 is the fundamental frequency. It's the lowest frequency that will produce a standing wave in that string under a specific tension. The node-to-node distance, so the length of an antinode, is lambda over 2, and the fundamental frequency produces a pattern with only one antinode. So we can calculate the wavelength using this relationship, or we could look at the pattern and then find the wavelength that way. So if this is one antinode, lambda over 2, we know that L equals lambda over 2, so lambda is 2L. So that's another way to think of this. Then for n equals 2, we would have two antinodes. So in that case, we would have L equals 2 lambda over 2, which is lambda. And then n equals 3, we have three antinodes, so L is 3 lambda over 2, or lambda is 2L over 3. And we could go on. So as we increase, every time we add one antinode. So if we wanted n equals 50, we would have 50 antinodes. Okay, and let's go over the labeling for these different harmonic frequencies. N equals 1 is the fundamental frequency. It's also called the first harmonic frequency. N equals 2 is the second harmonic frequency, and n equals 3 is the third harmonic frequency. Another term that's used to describe these harmonics is overtones. So anything above the fundamental frequency is an overtone. So n equals 2, since it's the first standing wave pattern above the fundamental, is called the first overtone. And then n equals 3 is the second overtone, and so on. So the overtone number is one less than the harmonic number. So it's just another way to describe these patterns.
Okay, so I've drawn out the normal mode patterns here since each harmonic number corresponds to a distinct normal mode pattern. And the number also here corresponds to the number of antinodes. So n equals 1 is one antinode, which has a length of lambda over 2. So you can either use the formulas as I explained or counting wavelengths to find the wavelength that corresponds with that harmonic. So I've just written the labeling out here so you can see we have the first harmonic and the fundamental frequency, then the second harmonic and the first overtone, since it's the first frequency above the fundamental that produces a standing wave, and then the third harmonic and the second overtone, and I could keep going. So that's how the labeling works. And here we could subtract any two consecutive frequencies to find the fundamental frequency. So f1 equals fn plus 1 minus fn. So that could be f3 minus f2, or f2 minus f1, or f51 minus f50, any two that are consecutive. There's two general ways to think about finding normal mode patterns in a string. So one way is to have a string of fixed length like this, and then to find each pattern we would adjust the frequency until we found that pattern, and then that would be the harmonic frequency. Another way is to have a string of variable length and keep the frequency constant. Okay, so in that case, if the frequency is constant, then the wavelength is constant as well. And what we can do is adjust the length in order to find these patterns. So if L1 is lambda over 2, then we would need twice the length of the string. We'd have to lengthen it in order to see the second pattern, which would have length lambda. And then we could lengthen it another wavelength over 2 in order to see the third resonance pattern here. So either way, we can find the three and then many more resonance patterns for that string. Example 9, a 2.5 meter long string is vibrating in a standing wave pattern with a frequency of 200 Hz. It is known that there are nodes at 1 meter and at 1.5 meters from one end of the string with no nodes in between. A, what harmonic is this? B, what is the speed of the waves on the string? Okay, so we have this pattern here. We don't know what happens yet after on either side, but one node is at 1 meter and the other is at 1.5 meter. And then the total length is 2.5, so we can kind of figure out what the rest of it looks like just because those are small lengths to work with. But we also know that this is lambda over 2, the node to node distance. So we have lambda over 2 equals half a meter. So lambda has to be 2 times that, which is 1 meter for the wavelength. And then we can figure out the harmonic by finding the number of half wavelengths that occur in this 2.5 meters. So if we take the full length and divide by that node to node distance, we have 2.5 divided by 0.5, which is 5. So we know that there are 5 antinodes. So n equals 5, or this is the fifth harmonic. Okay, and then with that we can find the speed of the waves on the string just doing v equals lambda f. So that's 1 meter for the wavelength times the frequency, 200 Hertz. So 200 meters per second. Example 10, a guitarist finds that the frequency of one of the strings is too low by 1.4%. Should FT be increased or decreased, and by which factor? Okay, so we want to figure out how the frequency depends on the tension. So we know F is NV over 2L, and we can plug in for the speed. Since it's a string, we still have the wave speed on a string here, which is root FT over mu. So plugging that in, all other factors are constant. N will be constant, L, mu. So we're just looking at F and FT, and we see that the frequency is proportional to the root of the tension. Or we could write that the tension is proportional to the root of the frequency squared. So one of the strings was too low by 1.4%. So when we tighten that string, we're going to increase the frequency. So we'll have F2 equals 1.014 F1 in order to get that to the right note. So that's what we want to happen. And so that means that our tension is going to have to change with the square of the frequency. So we'll have Ft2 equals 1.014 squared Ft1. And if we do square that, it's 1.028 Ft1. So what we find is that we need to increase the tension by 2.8%. in order to change the frequency by 1.4%. So we can see that they are directly proportional, so we knew we had to tighten the string in order to increase the frequency, and this tells us by how much. A string of length 25 centimeters and mass 3.2 grams, fixed at both ends, resonates with two successive harmonics of 159 Hz and 212 Hz. A. What is the fundamental frequency? B. What would be the necessary tension to produce a standing wave pattern with 3 antinodes? Okay, we have two successive harmonics. We don't know which ones they are yet, but we can subtract them since they're successive to find the fundamental frequency. So 212 Hz minus 159 Hz, which is 53 Hz. And that's the fundamental frequency. So then in B, when we're asked to produce a standing wave pattern with 3 antinodes, so something like this, then we have n equals 3. So we know that the frequency F3 will be 3F1. So 3 times 53 Hz, which is 159 Hz. Okay, so we can see that this was F3 there. And then what we want to find is the tension. So we'll need the wave speed to do that using F equals NV over 2L. We get, or 3V over 2L if we plug in that integer. So then V is 2LF over 3, just rearranging here for the speed. We can plug that in, so 2 times the string length, 0.25 meters, times 159 Hz, divided by 3, is 26.5 meters per second. Okay, and that's really what we need to then find the tension. So then, let's move that up. V equals root ft over mu. And we do need mu. I'm just going to plug it in and find mu at the same time. So ft equals v squared mu, 26.5 meters per second, mu squared, and then mu is the mass per unit length, so 0.0032 kilograms over 0.25 meters. So a tension of, this is really close to 9 newtons, 8.9888, so about 9 newtons is required to produce this standing wave pattern. There's more than one way to solve a lot of these standing wave questions because we can plug in formulas to each other or use the formulas in different orders or use counting on the diagram if that helps instead of the formula. So there's more than one way, but you should of course arrive at the same tension either way. Example 12, a standing wave pattern is observed in a thin wire with a length of 3 meters. The equation of the wave is y equals 0.002 meters sine pi radians per meter x cos 100 pi radians per second t. A. How many loops does this pattern exhibit? B. What is the fundamental frequency of vibration of the wire? C. Suppose the pattern is excited by a vibrator with a certain frequency. If the frequency was held constant and the tension was increased by a factor of 9, how many loops would be present in the new pattern? Okay, so we know that the length is 3 meters. Basically, we want to figure out how many antinodes, which again are lambda over 2, are in that 3 meters. So we need to find lambda first. That's our first unknown here. And we're given k from this standing wave function. We have k right here, which is pi radians per meter, and k is 2 pi over lambda. So lambda equals 2 pi over k, 2 pi over pi, so 2 meters. And then lambda over 2 is 1 meter. So that's nice, easy math. We have L over lambda over 2 to give us the number of antinodes because we have this total length and each antinode requires half a wavelength. So that equals 3 meters over 1 meter. So 3 antinodes or 3 loops. So this means that we're looking at the third harmonic. Okay, so for B, what is the fundamental frequency? We want F1. We're given omega, which is 2 pi f. So F equals omega over 2 pi. And this is F3, since we know that the function we had represents the third standing wave pattern. So this is going to be 100 pi radians per second over 2 pi. This is technically radians here. So we end up with 50 hertz. The pi cancels and we have 100 over 2. So then F1 is going to be F3 over, I mean to write 3 here, F3 over 3. So that's 16.7 hertz. So what I'm doing is using Fn equals n F1 in order to find F1, really what we're doing here, since each frequency is a multiple of the fundamental. Okay, this time we're keeping the frequency constant and increasing the tension by a factor of 9. So let's see how this will change the standing wave pattern. So if we could do that, the wave speed will change, of course, and we have v equals lambda f equals the root of ft over mu. Frequency is constant this time, so what will change then is the wavelength. Mu is constant as well, so we'll have lambda is proportional to the root of tension. And then tension's increasing by a factor of 9, so lambda will have to increase by a factor of root 9. So root 9, lambda 2 equals root 9, lambda 1. So 3 lambda 1, which is lambda 1 was 2 meters, so that's 6 meters. And so now this will change the pattern. We have 3 meters for the length. And then let's divide that. So 3 meters over lambda over 2 is 3 meters over 3 meters, since it's this divided by 2. So now this is one loop, like this. So if we change the tension in the string, then it's like we have a new setup, and there'll be a new set of harmonic frequencies that produce standing waves in that string. So this time, at a wavelength of 6 meters, we end up with the fundamental frequency, or the first harmonic pattern.
Standing wave patterns are important because it can be shown that at any frequency and any possible motion of the string, the wave function can be written as a sum of normal modes. And this is actually the basis of Fourier analysis. Also, these frequencies are called harmonic frequencies, but they're also called resonant frequencies. So at these standing wave frequencies, the system is in resonance. And this has similar characteristics to the resonance that we saw before. The system is oscillating at its maximum possible amplitude.